slope fields, fields of slopes. But if we had huge old tangent lines, what would be the problem if we had tons of huge tangent lines? It would all be ridiculously disgusting. So, since we're not going to have huge old fields of whole tangent lines, we're going to have fields of baby tangent lines. Look at your note packet, the one with all the wind pattern, or it looks like a weather report kind of thing. Zach, where's your note packet? The note packet, the one with the weather report. Lucy, where is your note packet? Get your note packet out. Come on, kiddos, we already announced this. Try getting it out too. Note packet, the one with the wind pattern on the front. It says notes on the top. It's supposed to be very, very easy to realize. This is the notes one, that one's the homework one. Does this one say homework? No, but this one says notes. Okay, so, on the notes one, do you guys see, you got it yesterday? Oh, you do have it, okay. So the notes one, the one that you got yesterday, you guys see that whole weather pattern thing below, right? What would happen if they showed the entire line, the entire trajectory of all those different little baby tangents?
They don't cry.
It would be a mess, right? But now that you're looking at it, question, can we kind of tend to follow the flow of what seems to be happening? Yes. Now, do they technically, in this picture, in this whole wind pattern, do they have little, what would I say, sensors in literally every single point of every single space that's covered in the map? No, they don't have little sensors in all those different places, right? Everywhere you walk, there's another sensor? No. So what's the idea of this entire map? Test at a few places, see the general flow, and then be able to understand how the wind is going to behave. This is one application of the slope field. There are others as well, but specifically in calculus, remember, differential equations are somehow involving derivatives, somehow asking us to go backwards from those derivatives, and then be able to consider the original equation. So for instance, in this one right here, when it gave you y equals cx cubed, it said, oh, it is a solution. It was, okay, cool, it's a solution, what else? And we were able to, once we knew that was a solution, we were able to check it by finding the derivative, plugging it in, saying, oh yeah, it does work, and then we went ahead and used the clue to find the actual equation. But the point is, once again, there are some differential equations that are way too complicated. And so the way of using a differential equation to think about an original without necessarily integrating, even though we'll be doing that at times, we will be integrating to go backwards like we've done all semester. Another way of using a differential equation is to make a slope field and follow the flow and say what equation seems to be flowing through these tangents, and to get an idea of the antiderivative that way. So what you guys already wrote down, it's not going to be in the debit card, don't worry. Some of you guys were a little bit worried about that. I mean, it could be, but I don't really want you to memorize it word for word. What I want you to be able to do is to make one and know how to use it, right? Not necessarily memorize it word for word. So the idea is you're given a differential equation. Some sort of derivative is involved in some sort of equation. For every point in the domain of f, now, are we literally going to be doing the infinitely many points for every function that we're trying to make a slope field from? No. Which is why, if you guys look at any of your packets, at any of the examples, you're going to see graphs with little points. They say don't do every single point possible, because that would be filled with points, right? So think dot paper. Maybe you saw it back when you were in like elementary math or like the very beginning of middle school math, but dot paper, we're only going to make baby tangents for the dots that are there. Do you guys see the worksheet, the homework one that I gave you? See, you're only going to put slopes for the dots or for the points that are there. So we're not doing every single point. We're not doing 1.1 and 2.777, no. We're only doing the points that are there. But we're going to assign a baby tangent, a small piece of a tangent line with a slope found from the differential equation. And so we will have, at that point, a little baby piece of the tangent line that would be skimming the curve that's passing through that point. This is what I put down as the steps for making it. I'm saving the table where you're plugging in the dy dx at particular points just to keep it all nice and organized. Sketch the baby tangents with approximate slopes, thinking rises over runs, but not connecting. Well, you'll see me do it. And then if you're given an initial condition, guys, ready? Initial condition, put a clue. Why am I saying put a clue? Because they've given you some sort of point in order to establish one specific solution instead of a whole field of solutions. If I told you on this wind pattern one to trace the wind, how would you trace the wind?
I don't know where to start.
Exactly, you don't know where to start. Could 12 of you, 4, 8, 12, no, sorry, 17. Could 17 of you trace the wind 17 different ways? Yeah. Because one person could start here and start tracing. One person could start there and start tracing. You could have different branches of the slope field. More complicated differential equations are going to have more complicated slope fields. It's not just the basic, like, oh, it's the same thing over and over and over again. In this one, it's like swirling one way around Syria and Iraq. It's swirling a totally different way around Iran. It's swirling a totally different way down in Saudi Arabia. Which makes sense. Wind is going to be different when you're in different places, right? But each of you can pick a different piece and swirl a different way. So the idea is an initial condition says, wait. Sketch the one that goes through that point, and so you all go to the same place. And in general, you sketch, for the most part, the same flow. So when we get to this example, this is the one that we were working on yesterday, the one that you were supposed to get up to in your notes. I started graphing slopes, but I didn't finish. Kiddos, how was I graphing slopes? Why did I put a flat baby tangent at 0, 0?
Because you plugged in the slope of there was 0.
Good. I plug in, I don't need the y, not in this one, but I could have plugged in the y if I needed it. I only needed x, I plugged in, the slope is 0. Question, where else would the slope be 0?
At any other point along the y-axis?
Yeah. What if I had chosen, instead of 0, 0, what if I had chosen 0, negative 1? Wouldn't that also be x equals 0? Or what if I chose 0, 1? Wouldn't the slope, it's only dependent on x, aren't all of those x's 0? So what can I now do for all the other ones?
You can make them all
Along the x equals 0 line. When a differential equation is only dependent on an x, when it only has an x inside, all vertical lines, or all the slopes will go in vertical lines. So guess what? Where else can I put, well hold on, pause. How did I get it sloped this way? Why isn't it steeper or why isn't it less steep? What's the slope at 1, 0?
Slope 1.
Positive 1. Do you guys see how I did it?
Yeah.
Would positive 1 be up 1, over 1? Wait, why didn't I connect? No, baby tangent. So I went up 1, over 1, and I thought dot, connect. Dot. Right? What if the slope was 2, which it's not, but what if the slope was 2? Up 2, over 1, connect, a little bit steeper. If it was 3, up 3, over 1, approximating, a little bit steeper. Now at some point, is it going to get hard because, well, my marker is pretty thick compared to your pencil? Yes. And for you guys, what's the difference of the slope of 10 and the slope of 50 going to look like? Not much. They're both going to be really steep. So sometimes you just kind of say, I don't know, a little steeper, and then you're like, okay, whatever. Eventually you're going to make it looking straight up, but question, can we ever technically truly get to straight up?
No.
So if there ever was a place that was straight up on a graph that's given to you, it's probably a horizontal asymptote. Sorry, vertical asymptote. So what am I going to do with all the different points that have an x of 1, including 1, negative 1, and 1, 1, and 1, 2, technically? All the x's are 1, so all the slopes are up 1 over 1. Up 1 over 1. Up 1 over 1. As I finish this one, ready guys, in your notes packet, I think, don't you have an example that's asking you to make a slope field? It's a different example, but that's okay. You look at the very bottom, example number 1. Oh, there are no points. The notes packet. Good. The notes packet. The one that says notes. All right, go find example number 1. There are no, oh, nope, example number 1. There we go. Okay, there are no points. Where do you think I want you to choose the points? Every single whole number. Every single whole number, don't go fractions. So, what points do I see? I see 0, 0, I see 1, 0, 2, 0, 1, 1, 1, 2, 2, 1, 2, 2. Make a table. Make a table with your points and with your derivatives. Uh-oh, hold on, the differential equation. Hey, it's the same one as mine. Ready, set, keep going.
It's like a blank sheet.
That's fine, David. Let's
Go
just
get
draw it on, David.
Shh, go get another one. It's okay. I think I have a couple actually. That's fine. Sorry about that. Every now and then a copier makes a mistake. Copier person or the copier itself. But
We should fire both of them.
let's not. Shh, baby tangents. You guys have even more than I do. So I'll do a few more just to try to model. But you guys, you're also supposed to do -2 and 2, yeah? Tell me when you get over to when x equals 2. What's the slope when x equals 2 or negative 2? I like negative 2. 1, 2. Did you guys think about going 4, 1?
Yeah.
And then connecting? It's supposed to be steeper, right? The AP graders, if there's one of these, will not be actually measuring with a protractor if your slope is accurate.
Yeah.
It's just going to say, did they get steeper? Yeah. Oh, good.
Substantially.
Oh, sorry. Does the whole trick of seeing that since this differential equation is only dependent on x's, that the slopes follow vertical lines, does that save time?
Mm-hmm.
What do you think is going to happen if this was to be y squared instead? The slopes wouldn't follow vertical lines. What would they follow? Yeah. And what if there are x's and y's? Something like Saudi Arabia, Iraq, and Iran, where all the slopes are kind of different. Doesn't mean there's not a pattern, but it's not going to be as easy to see. Okay. Did we get it okay?
Yes.
So, what if I was to ask you? Does it ask you? Oh, it doesn't. That's lame. Does it ask you later? Nope, still doesn't. It does give you a few more directions as far as a few more words if any of you guys want to keep looking. But, what if I was to say, sketch the antiderivative or the solution to the differential equation that goes through the point 0, 1. How would you follow the flow? Connect the dots? No, it's a flow. It's not supposed to be all these lines.
It kind of looks the next cube function, but
Doesn't it kind of look cubic?
yeah.
Which would make sense.
Why would it make sense?
Well,
Because
it's
it's different.
If you multiply the dx and you actually integrate, what's the integral of x squared? 1/3 x cubed. Now, does your slope field give a great picture? It's okay. Turn the page. This is computer generated. It shows all kinds more slopes.
Oh, yes, this is slightly better.
It shows all kinds more slopes. Is it a little bit nicer to follow the flow on this one? A little bit easier, right? Does it still look cubic? And the answer is hopefully yes. Guys, example number 2. Differential equation changed just a little bit. Now you have x plus y. Ooh, so is this going to follow vertical lines?
No.
Horizontal lines? No. It's going to be mixed up. Now, this is just our clue. So eventually we're going to follow the flow using that point. But what do we have to do first? Get a slope field.
Let's go out of warrior.
All right, kiddos. If you can mental math it, maybe you don't need to make a table of every single point. Ooh, how many points are on here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. 35 different points. Do you think I'm really going to write 35 points here? No. But I'm going to write a few just to get you guys going. My dy dx or my y prime is equal to x plus y. In a differential equation, get the slopes, you got to get y prime alone. But then when I plug, wait. 0 plus 0 is equal to? All right. So that one's flat. What if I was to plug in 0, 1? 0 plus 1 is 1. Okay, so 0, 1, I'm going to up 1 over 1. Little baby tangent. Oh. It wasn't flat. I liked following the vertical lines because it was fast. Guys, is there going to be a point where it is going to be flat? Where the slope is going to be 0 again? When x and y are the same, but one's negative, right? Give me an example. What's the point where x and y are the same, but one of them is negative? How about negative 1, 1? Or 1, negative 1? Oh, so negative 1, 1, that's going to be flat. And 1, negative 1, that's going to be flat. Hey, what else? How about 2, negative 2? How about negative 2, 2? How about negative 3? Oh, it's not there. Okay, well, that kind of did a little bit. Question, are there any other points that are going to have the slope of 1? How else can we get 1? 1, 0. That works. 1, 0. There we go. Up 1 over 1. What else adds to be 1? Negative 2, 3? Uh-oh. It's not on the graph. Otherwise it could be. Oh, wait. What about negative 1, 2?
Yeah.
Oh,
Negative.
okay, up 1 over 1. How about 2? 2 plus what would be 1? Question, do you see how there's a pattern? Oh! Hey! So, question, what would the slope be at 2, 0? Well, 2 plus 0 is... Right? But wouldn't 3 negative 1 also be 2? Wouldn't, negative 1, 3? How about 0, 2? 0, 2 would also be 2. Okay, so 0, 2, that's going to be up 2 over 2. I don't know, it's a little bit steeper than 1. Up 2 over 1, sorry, up 2 over 1. Up 2 over 1.
How do you do negative?
Up 2 over 1. Let's finish the first quadrant because we're almost done with that one, right? What other points do we have? How about 1, 2? That'd be 3, right? Up 3 over 1. I don't know, it's a little bit steeper than 2. I'm cheating, I know. 2 1's gonna be a little steeper. You guys see how I'm just following diagonal lines now, right? If I go to 2, 2, that's gonna be 4. Okay, fine, it's a little bit steeper. 3, 2, that's gonna be 5. Okay, a little bit steeper. See how it just starts getting steeper and it's hard to tell the difference.
Yeah.
There's a slope of 1, there's a slope of 2, there's a slope of 3, and 4, and 5. Okay, we're just getting steeper. What have I not done yet? Hey, what about 1, negative 2? Nathan was like, how do you do a negative slope? 1, negative 2 would be negative 1.
Instead of up.
Just go down 1 over 1 and go back. Right? Ooh, can I follow that diagonal line?
Probably.
0, negative 1? Oh yeah, down 1 over 1. Sweet. What else am I missing? Negative 1, negative 1. That'd be negative 2, right? 1, 2 over 1. Negative 1, negative 2, that'd be negative 3. That's hard. Let's go up 3. 1, 2, 3, and back 1. Guess what's going to happen if you guys have found the pattern? It's just going to get steeper and steeper. You guys get the idea how we're taking points one at a time. Like the point, for instance, the one I just did, negative 1, negative 2. We plug into the differential equation which says add the two together. Negative 1 minus 2 has a slope of negative 3. I came down here and said negative 1, negative 2, slope of negative 3. I didn't like going where there weren't dots. So I went backwards, 1, 2, 3, up 3, left 1 will also give a negative slope. And I pretend like I'm connecting. I draw it solid here. And I don't truly draw anything for all the dots up there. Does that kind of make sense? Now, are we done?
No.
What do we do?
Yeah.
Find the point.
Line with graph.
Which point? 1, 0 or 0, 1?
0.
Good. Y of x, 0, 1. Follow the flow. When I see a tangent line, it's supposed to skim there, right? It's supposed to get steeper. But wait a minute, how do I have to connect all these guys?
There's a graph.
Follow the flow. Sure seems that it comes in this one. If you were to have way more points, you would see it coming up, flowing this way, whereas if you were over here, then it'd be flowing that way. Remember, the Saudi Arabia, Iraq, Iran, depending on where you start, you can end up very different places. You don't have to connect every single arrow, every single tangent line. Follow the flow. I don't know, it's going up. Wait, and then it's, oh yeah, I'm not even supposed to be on that side. Okay, cool. Follow the flow. Guys, just a heads up. This differential equation, right here, the x plus y, impossible for you guys to solve. Impossible for you guys to solve. Because if you tried to multiply the dx on the other side, I'll show you real quick. Impossible for you guys to solve. Wouldn't we multiply the dx to move it over? Yay! Integrate both sides! Who doesn't belong?
About y.
Well, why?
Oh, subtract him. No, it's illegal.
Just
We
ask a
multiply.
BC kid.
No, don't even ask the BC kid. They can't integrate this either.
Oh.
Maybe a multivariable partial integration?
Master.
Maybe. I haven't done these in forever, so I'm just making up stuff now. But I think it might be a double or triple integral, but you can't subtract the y, because it's stuck. Oh, divide the y, but then you all of a sudden have a y here. It's stuck. You cannot, by AB or even high school calculus methods, solve that integral. Well, then how do we know if we are given some sort of differential equation like that? How do we know what the original is doing? Hey, look, it flows like that. Yeah, go team. Does that answer all the questions? No. Does it give us an idea of what it is? Yes. Interesting. All right. Example 3. What would you do to solve it? Hey, yes, look at this guy. Isn't he small? Is he tiny? This is more like the size that they would give you on an actual FRQ part. This is more like the size they would give you. They could give you maybe a few more points, but example number 2 is a bit extreme. It's usually either this size or just a little bit bigger. Guys, get ahead of me. Sketch the whole thing. Get ahead of me. Sketch the whole thing.
Oh, it's dreadful.
Oh, come on. How about that? You only have 9 points to plug in. You can make a whole table from this one. You guys agree mostly? Sketch a solution that goes through the origin, right? How easy is it to figure this guy out?
No.
Seems like maybe there's this 0 thing going on, so maybe I'll make it go flat.
Is it like
And then somehow maybe it seems to be going up,
But then it like,
and then maybe it goes flat because of this 0 thing, so maybe it goes flat. Like all of these are 0.
so it doesn't go 0 again? It looks like it would.
Don't the zeros seem to be diagonal though?
Yeah, I
Which
guess.
means the 0, the flat line would be here, if I kept doing these. It's hard to see though, yeah? Okay, look down below. What if there are tons more points?
That's easier.
Which, how much time would that take?
A lot.
A lot, unless you learned how to code and you make a computer program, or steal from someone else and then use their program. But anyway, you guys get the idea that it's a lot easier when you're graphing by hand or making a slope field by hand to only have a few points. But in the long run, that doesn't give you a great picture unless you have a lot more points. We would use technology for that. So, just to get the idea of a slope field, being able to do it by hand, having a few points. Hey, what's the beginning of your worksheet again? The homework worksheet? Making slope fields. Yeah? Do you have to show me a table with all the points? No. No, you don't. But you need to get better at making slope fields pretty quickly. And if you were given, say, an FRQ, one like this with 9 points, you might want to show a little bit of work. But the long story short is you just have to get it down as far as carefully plugging in, doing the mental math, and making the baby tangents. All right, the problems all of a sudden change. Woo-hoo-hoo. The problems change. All right, this is nice. Guess what? We don't have to make any slope fields this page,
Yay.
but we have to still understand them.
Oh.
Example 4 says, match each slope field. Oh, hey, they're done for us. With the equation of the general solution it could represent. Slope field. Remember, dy dx actually solves for the numeric values of the slopes. The general solution, which would be like the y equals f of x, the general solution, you have to look at the flow. So the dy dx gets us the actual slopes. The general solution follows the flow. So kiddos, if I'm trying to figure out which of these goes with Roman numeral 1, does it make sense? Wait. Hold on, think of all these guys. Wouldn't he just be a horizontal line?
Yeah.
He would just be a diagonal line. He would be a parabola. He would be some sort of cubic-y guy. He would be some sort of 1 over x squared guy. Hey, basic graphs coming in handy.
Oh.
He would be some sort of start in the middle and then go. He would be some sort of start at the top and then go. And he would be some sort of what? ln of absolute value of x. Absolute value says on the right and on the left. All right, cool kids. What's number 1 seem to go with?
Sine.
No,
Not
sine,
cosine.
not cosine,
Because
because if it was
look.
cosine, it would be 0.
If you were to choose a point, couldn't you follow the flow? That looks like cosine to me. Sorry, that looks like sine to me, right? Sine starts in the middle and goes up. Cosine starts immediately going down. Yeah, sine starts in the middle, goes up. Cosine starts immediately going down. So this one we have to go with letter F. How about this guy? The only one that makes sense would be D. Because if I was to pick a point and follow the flow, doesn't it look kind of like a cubic-y guy? All right, example number 5. I'm not going to draw all the sketches. You guys know, follow the flow. These are y's, not dy's. We're not looking at the slopes themselves and the number values of the slopes, looking at the flow. Who flows through this guy? If you need to, choose a point, follow it. Come on, basic graphs.
E.
Has to be E. Nothing else makes sense. Cosine, there's no like periodic-y thing going on. E to the negative x, I don't know, some sort of swoopy. Well, okay. It'd be an e to the x swoop, but the other direction. E to the x, well, that's a normal swoop. X squared, well, that's a parabola. None of those make sense except for our. You guys get the idea? Example number 6. Ready? Wait. Hold on. What are we matching with this time? And the derivatives, think about your tables. Don't the derivatives actually determine the slopes themselves, like the number slopes? Can I help with this a little bit? As I look, remember how we really liked the ones that followed vertical or horizontal lines? Because it'd be so much easier to graph or to sketch. We did an example number 2, and it followed, if you guys want to look back, example number 2 followed vertical lines. Nope, example number 1. Example number 1 followed vertical lines. Why? Because its dy dx only had what variable?
X.
It only had x's. Do you see any other graphs up here that only follow or follow vertical lines?
Yeah. E.
Not E. Careful, it changes as you go in the vertical line. B. Same. When x equals 0, all the slopes are, what are these slopes? 0. When x equals 1, well, it looks maybe like 1-ish, then 2-ish, then 3-ish, then 4-ish. Hey, which of these, first of all, only has an x in it? 4, 6, or 1? 4, 6, or 1? I know one of those has to match with B. Are there any other ones that follow vertical lines?
D.
Ooh, D does. Look, see? When x equals 0, dy dx equals 0. Uh-oh, so I have 2 of them where x equals 0, dy dx equals 0. What other one follows vertical lines? You see them? parallel, 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 parallel. Now, I don't know exactly what this is, but I do know when x equals a certain constant, dy dx is equal to a constant also. So when x equals some sort of thing like -1, dy dx is equal to some sort of, I don't know, positive number. Okay, kiddos, let's think through this. If I have 6, 4, and 1, can anybody do, by process of elimination, figure out who B or D or F goes with?
Yes.
Okay, who does D go with?
Who goes with,
D has to go with 6. Why? Doesn't this look an awful lot like something sinusoidal? More specifically, guys, you know sine of x. What would his solution, remember, follow the flow, look at the solution. What would his solution end up being? Negative cosine of x, right? Ooh, so this isn't just any sinusoidal, it's a cosine, but either way, whatever, it's sinusoidal, it has to go with the trig one.
Sinusoidal.
So question, now we have 1 or 4 going with B or F. Who can narrow down another one? John?
letter F goes with 1.
Yes. Can you guys follow the flow of this guy? Wait, that's not right! No. That e to the x, that's not supposed to be the flow, that's supposed to be the slopes, right?
But its derivative is itself.
Its derivative is itself, which means if I was to solve this guy for the original, wouldn't y also be an exponential? That's exactly why number 1 does need to go with f. Well then, by process of elimination, what does number 4 have to go? Pause. If you were to solve this guy, wouldn't this be an x squared? Follow the flow, what does this guy kind of look like? A parabola. Yes, this guy's an upside down cosine, which makes sense. If you were to follow the flow, it's a horrible following the flow, but whatever. Okay, who do we have left? A, C, and E. And we have 2, 3, and 5.
E kind of looks like it has like a slant asymptote.
So it's
But
over.
probably not. I don't know.
No, because there
E kind of looks like a slant
That's what it
asymptote.
looks like, but
It doesn't exactly, well, we wouldn't be able to see the function to see the slant asymptote. Does that make sense?
you know.
Well, if you look
Because remember, number 3, oh, no.
already.
Number 5 is impossible to solve. Number 3 is going to be something logarithmic. We haven't actually solved enough for you to know that, sorry. And number 2 is interesting. Why am I going to really quickly come over to number 3 and say, haha, it's A.
Because you can.
This horizontal.
It's following horizontal lines, and this is the only one that only has,
Oh, what?
you guys see it? At this one, you can also say, wait a minute, if y is, I don't know, 1 or 2-ish, something like that, if y is like 1 or 2-ish, dy dx is equal to 0. Does that make sense with, oh, yeah, okay, if y is 2, that makes sense. 2 minus 2 is equal to 0, but either way, if y is equal to some sort of number, the horizontal lines will follow. I was able to do that one real fast. Okay, we're between E and C. He's kind of hard to figure out where everything is, right? But I love E. Why do I love E? What do I see?
You see 0.
I see zeros. And when do the zeros seem to be happening?
At 1, 1, 2, 2, when y equals x.
Is there anything that would make sense that when y equals x, or at least when x is a positive and y is a positive, somehow they cancel out? See it? When x is a positive, y is a positive, they might cancel. Now let me give you a hint as to how you could match C. Do you guys see how in the first quadrant, do you see how all the slopes are positive?
Yeah.
What's true about x's and y's in the first quadrant?
They're both positive.
Does this make sense? If I plug in a positive over a positive, it'll always be positive? Huh. I can even plug in little points like, hey, what happens if I plug in 3, 2, or what happens if I plug in 5, 3? I could say 3 over 2, 5 over 3, you might be able to see, oh, hey, it's also getting steeper, but steepness is kind of hard. Signs and directions are usually easier. For instance, what's going on in the second quadrant? Slopes are all negative. Well, aren't the x's negative in the second and the y is positive? Does that make sense that a negative over a positive will always make a negative? So that's also another way for you guys to deduce, is actually looking at the signs themselves in general in the quadrants. But the other way is that you could have literally picked a point like 2, 1 and said, oh, 2 over 1 is a positive 2. Oh, it's positive. Whereas over here, if you picked 2, 1, you might actually end up with a 0 with a negative. Well, that was negative. So sometimes you plug in points also. There are lots of different strategies for matching. That gives you a little bit of experience. Here's the different possible questions that you guys might get having to do with slope fields. Your different possible equations that you guys might get having to do with slope fields. You might be given a differential equation. I'm just trying to get your brains used to what might be given to you. You might be given a differential equation, which would be like a y prime equals or a dy dx equals. They almost always put it in the dy dx form, but it could be y prime if you're looking at like other problems, non-AP problems. And you could need to choose a slope field. In which case I would say, consider the number values of the slopes. Like we did in the example before. When are the slopes 0? When are the slopes positive? When are the slopes negative? If you plug in the dy dx, it needs to match. Consider the actual number values of the slopes, or the signs. Number values and signs of the slopes. If they give you a solution function, and you're choosing a slope field, you get to just consider the flow. Because that solution function needs to flow through. Needs to flow through that slope field. You can also think about the antiderivative. Oh no, they're not giving you the differential equation. Sorry. They're not giving you the differential equation. They could give you a slope field and then say choose from all sorts of different differential equations. In which case I would probably try to say, think number value signs of the slopes and or antiderivative flow. But warning, remember we can't always antiderive. Whenever there's an x plus a y, x minus a y, some sort of plus or minus with x's and y's, it's impossible for us to antiderive. Some AP questions make you want to antiderive, but you cannot. So only think of the antiderivative flowing through if it's able to be antiderived. And last but not least, what if they say, given a slope field equation, choose the solution? Once again, just consider the flow. There's something down below, just letting you guys know that technology, there are definitely programs. There's even like a TI. You guys, if you search TI programs online, you could find a slope field program. We could download it on your calculator and you could actually like plug in a dy dx and get a slope field. Or plug in a y and get a slope field. It's not a bad thing to have, and maybe before the AP I'll try to get it on your calculator. But for right now, you could just go to Wolfram Alpha and say slope field of. You can check it out that way. The problem is getting programs on your calculators. I have to get basically the equivalent of an aux cord out, and I have to single-handedly, or with just a few of you guys helping, take one calculator onto everyone's and download it. It doesn't always work. Anyway. Is it okay if we just say Wolfram Alpha, you can find a slope field if you need to check an even or something like that? Okay. Technology definitely can make slope fields for you. As you can see, a lot of this worksheet was made with calculator programs, probably even the TI program that I use, like dragging and dropping different calculator windows. But long story short, you're going to have to be able to do this by hand. The matching and the sketching. Okay? You guys still working on it at all? Okay. Let me give you a second. Let me freeze the screen. I want to see if there's anything else specifically for book work that we should go over. We've done the main idea of slope fields. Yeah, I just have lots of different worksheet examples that we're going to work on tomorrow. Basically, my agenda. Let me go ahead and do a dual page so you guys can see the very last page, which is just basically hints that I used when matching. Here are hints when I used when matching, where slopes are 0. As I fill in these hints, my goal tomorrow is basically to bust through the notes worksheet as much as possible. Get as many examples done. Matching, some FRQ ones. There's all sorts of different examples because this shows up not every year, not even every other year, but it shows up frequently as you look at all the different APs over the past 20 years. Actually, it's been longer than that, but you can see slope fields come up fairly often, and if they don't show up, the ideas behind them, like solving differential equations, will always show up. So we're going to do as many examples as possible in the notes tomorrow. Our goal, finish the notes tomorrow. For tomorrow, I want you guys to have the book work fully attempted. Get into the book, those are like the basic problems, the non-AP-ish problems, but get into the book. If you have time, maybe start the worksheet, because it's going to be due the next day. Start the worksheet just sketching. Just sketching, you're really good at sketching. If I say, if you start the worksheet, just do all the sketching. That'll be a nice load off your back for tomorrow night. Play with sketching, play with the book work. Come in tomorrow with things you get stuck. And hopefully by doing more examples, we'll answer those questions. Sound good? Okay. Slopes along the x-axis. For all the x-axis, that would be when x equals 0. dy dx equals, and then you have to think about it. Sorry, when y equals 0, I wrote that totally backwards. X-axis is when x equals 0. Different things you would just think about as far as solving. Only dependent on x, those would be following vertical lines like we saw. Only dependent on y, following horizontal lines. And then where the slopes are positive or negative, I would say check the signs of the quadrants. But anyway, those are all just things that I use. I wanted you to have like a little quick summary so you can look at it if you do homework tonight. Alright, kids, good job. Tomorrow we'll bust out as much practice as possible and try to master this stuff.